Welcome to Manufacturing Processes, Machining and Machine Tools lectures by Professor Joyjeet Ghose. This is the 14th lecture of a series of lectures. This lecture will be on milling indexing, part 1. He will be discussing about dividing head, different types of dividing head like plane dividing head and universal dividing head, construction of universal dividing head, types of indexing methods like direct indexing, plain or simple indexing, compound indexing, differential indexing, angular indexing are also discussed with solved examples. In this lecture, solved numerical on compound indexing is discussed. So, do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access all the videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to this lecture. In this lecture we'll be discussing about milling indexing. In fact, milling indexing lecture will be divided into two parts. In the first part we'll be discussing about universal dividing head, plane dividing head. We'll discuss up to the compound indexing method, and differential indexing and angular indexing will be discussed in the next lecture. So let's start. We'll start with what is a dividing head or indexing head. Or what functions does a dividing head or indexing head does. The main function that a dividing head or indexing head does is that it divides the workpiece in equal number of divisions. That means basically after each cut it will enable the setting up of the job which is in a new angular position, and automatically or manually it will move the workpiece through a certain angle as is required to divide the workpiece in equal number of divisions. So that is dividing head or indexing head. Now it can be of various types: plain dividing head, universal dividing head, and optical dividing head. Optical dividing head will not be discussing in this lecture. Our discussion will be focused on mainly on universal dividing head with an introduction to plain dividing head. Plain dividing is very simple and does not need much discussions on it. Rather, we'll be discussing in details on universal dividing head. So let's start with plain dividing head. Basically, in plain dividing head, on the spindle which carries the workpiece, there is a plate, and that plate has 3 whole circles, 24 whole circles. That means there is a circle in which in circular manner there are certain holes. So there are 24 holes in the first circle, and 30 holes in the second circle, and 36 holes in the third circles. Now these holes enables us to divide the workpiece in the factors of this particular number of holes. That means the factors of 24 are 2, 3, 4, 6, 8, 12 and 24. That means we can divide using this particular 24 whole circle. We can divide the workpiece in this number of divisions, that is 2 divisions, 3 divisions, 4 divisions, 6 divisions, 8 divisions, 12 divisions and 24 divisions. Likewise for the other circles, whole circles also, like 30 and 36. Now how do we do it? We do it using a spring loaded plunger. So first, the plate is directly mounted on the spindle. So as you lock a particular if you lock the plate at a particular hole in a particular whole circle, that means if I lock it in a, let's say, 24 whole circle and take a cut, then we remove the plunger and let's say we rotate 6 holes in 24 whole circles, and then again we lock it there, and this we continue 4 times. That means dividing the workpiece in 4 number of divisions. Okay, so for dividing the workpiece in 4 number of divisions, we have to move 6 holes in 24 whole circles. That means the numbers is basically, the number of holes to be moved is basically 24 divided by n, or 30 divided by n, or 36 divided by n. That is the formula for calculating the moment in plain dividing head. Likewise, if you want to divide the workpiece in 3 number of divisions using a 30 whole circles, then you have to move 10 holes in the 30 whole circles after each cut. So 30 by n, that is 30 by 3, that is 10. So you have to move 10 holes in after each cut. Okay, so that is about plain dividing head. This is a universal dividing head. Okay, uh, notice that this is the spindle, and this spindle is mounted on a worm wheel, and that worm wheel messes with the worm, and the shaft carrying that worm messes with shaft carrying that worm has this index crank. This is the index crank, which is a radial slot. That means the index crank can be readily move in or out and can be locked. This is a plunger pin. The plunger pin can be locked in any one of the whole circles. In any one of the whole circles, you can lock it at any one of the whole circles. Okay, this is a universal dividing head. In this dividing head can be tilted also. That's why it is graduated in degrees. Normally, we don't have this tilting type. Okay, and there is a plate here. This is, I think, 24 whole circle plate for direct indexing. So we'll discuss direct indexing later. So this is a Fostex universal dividing head. Okay, this figure I've taken from P&R book. So this indicates this the one that I've shown you. This is the spindle. This spindle is mounted here. This spindle is mounted here. Sorry, mounted here on this spindle. On this spindle, the worm wheel is mounted, and this is the worm. The worm is mounted on a shaft which is called worm shaft. On this worm shaft, the index crank is mounted. This is the index crank. This is the index crank. There is a radial slot by which we can move in and out. And these are the sector arms. And this is the index plate. The index plate is mounted on a slip. The index plate is mounted on a slip. The index plate is mounted on a slip. So movement of the index plate is independent of the movement of the shaft. Or rather, we put in other way that if this crank or the worm moves, then the plate will not move. Okay, so and there is a bevel gear mounted on this slip, not on the shaft. This is mounted on this slip. Okay, we'll discuss the function of the bevel gear later. So this is the worm. This is the worm. This is another picture, isometric drawing here, and this is the index plate. This is the index plate here. This is the index crank, which can be readily moved and out in this slot and can be fixed at any particular hole. The sector's arms are used for referencing. This is the worm wheel, and this is the spindle on which the workpiece is mounted. The worm has 40 teeth. The worm wheel has 40 teeth. Sorry, the worm wheel. This wheel has 40 teeth, and therefore, if we rotate the worm by one rotation, the worm will rotate by 1/40th of a rotation, and if you rotate the worm by 40 rotations, the worm will rotate by one rotation, that is the workpiece rotated by one rotation. So please remember this. There is no reason why it is 40. The initial Brown and Sharp universal dividing head at 40 teeth, so it is continued like this 40 teeth. This is the standard, but there is no particular reason why it has 40 teeth. So if you rotate it by 40 times, the worm wheel rotates by one time, and the workpiece rotates by one time. If you rotate by one time, it rotates by 1/40th of rotation, and the workpiece will rotate by 1/40th of rotation. Please remember this construction of the universal dividing head. Without understanding the construction of universal dividing head, you will not be able to understand the indexing methods. Okay, so this plate, Brown and Sharp plate, has three. Brown and Sharp dividing head has three plates. Plate 1 has 15 whole circles, 17 holes, 15, 16, 17, 18, 19, 20 whole circles. Like that, there are 6 whole circles in each of the plate. There is another type of dividing head which is called Cincinnati-Parkinson's. In Cincinnati-Parkinson's also there are 3 plates, but these 3 plates have whole circles on both sides. Okay, so these have whole circles on both sides. So whereas in Brown and Sharp we have on one side, and therefore the number of divisions possible by Brown and Sharp is less. In India, we mainly use Brown and Sharp dividing head, and therefore the index plates are Brown and Sharp. So our discussions will be mainly restricted to Brown and Sharp type of dividing head. Okay, so it is better if you remember these whole circles in the plates 1, 2 and 3 of Brown and Sharp. It will help you to solve the numericals. These are the whole circle. The innermost has 15 holes. You can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 holes are there in this 15 hole circle. Likewise, 18 holes are there in 18 hole circles. Likewise, 18 holes are there in the 18 hole circles. These are the index plates. You can see the index plates here. This is a tail table. This is the tailstock. So the work will be held between the headstock and the tailstock. This is the dividing head will be act as a headstock, and this is a tailstock. These are the change gears which will be required. Okay, so this is these are the gears used for differential indexing. Universal dividing head has the following functions in conjunction with the tailstock. It acts both as a holding as well as supporting device for the work during the operations. It sets the workpiece in desired position in relation to the machine table. After each cut, it rotates the workpiece to a desired angle, thus indexes the periphery of the workpiece in the required number of divisions. It provides a continuous rotary motion. This is particularly required in machining helical grooves on the workpiece. Normally, we don't use it until unless we require to produce a helical groove. What are the indexing methods? So different indexing methods are there: direct indexing, plain or simple indexing, compound indexing, differential indexing, and angular indexing. In this particular lecture, we will be discussing direct indexing, plain and simple indexing, and compound indexing. Differential indexing and angular indexing we will be discussing in the next lecture. So direct indexing. In direct indexing, if you look at these, this plate is used for direct indexing, and you can notice that there is a plunger here. The plunger can fix at any particular hole and you can do the work. So normally there are 24 holes are there. So 24 holes, the fraction of the factors of the 24 can be divided using this plate. So directly mounted, lock it and rotated by the number of divisions. So 24 by n is the formula for direct indexing. 24 by n, and we can divide it for plain and simple indexing. Okay, so here we know the worm wheel is directly mounted on the spindle. So if you rotate the crank by 40 rotations, the work rotates by 140 by 1 rotation. If you rotate by 1 rotation, the work will rotate by 1/40th of rotation. Now if you rotate the crank by 2 rotations, the work will rotate by 1/20th of a rotation. So therefore, if we rotate the crank 2 times, then we can divide the workpiece into 20 divisions. That means two full rotations, take a cut, again 2 full rotations, take it 20 times, make it 20 times, and you can divide the workpiece in 20 divisions. So likewise, if I want to divide the workpiece in n number of divisions, then we will have to the formula is 40 by n. So for each divisions, 40 by n, we have to move the index crank 40 by n for each divisions. Let's say if we want to divide the workpiece in 23 divisions, then the index crank movement would be 40 by 23. Now we have a whole circle 23 in the BM. This is a 23 whole circle is there in plate number 2. So in this whole circles 40 by 23, that is 17 by 23. That means we'll move, this is not here, let's say we'll move 17 holes in 23 whole circles after each cut. And how many times will repeat? We'll repeat it 23 times. So this is required for 1 divisions, and for 17 divisions, for 23 divisions you have to repeat 23 times. So how much you have to move? 1 complete rotation and 17 holes in 23 whole circles. You can use the sector arms as a reference. We can set it to 17 holes in the 23 whole circles, and we can rotate it. We can rotate a full rotation and 17 holes in 23 whole circles. How many times? 23 times for 23 divisions. So one more example, if we take 60 divisions, so 40 by 60, which comes out to be 2 by 3. Now 2 by 3, if we multiply it by 6 by 6, it comes 12 by 18. So this is the first plate. We have 18 whole circles. We have to move 12 holes in 18 whole circles. Or you can move, if you multiply it by 5, 10 holes in 15 whole circles. 5 by 5. So you can move 10 holes in 15 whole circles. Or you can move, multiply it by 7, you can move 14 holes in 21 whole circles. Likewise, if you multiply it by 11, 22 holes in 33 whole circles. The multiple solutions are possible. We have to maintain the fraction. That's it. We have to maintain the fraction, and you can move any holes in any whole circles. That is up to you. But the fraction has to be maintained. This is how we do simple or plain indexing. Now, sometimes the number of division is such that it is not possible to simple or plain index. So then we go for compound indexing. In compound indexing, what we do is that we move the crank according to the number of divisions required. Then we add or subtract certain divisions by rotating the crank and the plate in same direction or in opposite direction. I repeat, in compound indexing, there is a compound movement of the index crank moving in a particular direction, and then we move the index crank and the plate both in same direction or in opposite direction, depending on the amount we have to subtract or add, or amount movement we have to subtract or add. Okay, so that is called compound indexing. We'll tell you how it is possible. Let's say in a compound movement we move 3 holes in 18 hole circle, the index crank, and after that the crank and the plate both we move 5 holes in 20 hole circles. Now here in same direction, so 3 by 18 plus 5 by 20, if we do it simplify, we get 5 by 12. So 5 by 12 means 1/96th of a revolution. That means we can, if we give this movement, this compound movement, we can divide the workpiece in 96 divisions. Similarly, if we move in opposite direction, it will be subtracted. This, if you simplify, it comes out of 8 by 45, which is multiplied by 45 multiplied by 40 will be 1 by 225. So 225 divisions are possible if we give this compound movement. Now the question is how to find out this compound movement for this particular number of divisions. This is, I have done it in a reverse way. If this is the compound movement, this is the number of divisions possible. Now we have to do it in the reverse way. That is, the number of divisions will be given to us. We have to find out the compound movement. So for that we have this formula. So first we have to select any 2 whole circles on the same plate and on the same side. Very important. It should be on the same plate. We cannot select a whole circle from plate 1 and another from plate 2. That is not possible. Please. Very careful while selecting the 2 whole circles. The 2 whole circles should be on the same plate. And if you are using Parkinson's plate, then it should be on the same side also. So first we have to select 2 whole circles. Now the question is how to select the whole circles. We'll come to it later. In the second step, we have to find out a fraction. The fraction is basically factors of divisions required into factors of difference of the whole circles divided by factors of 40, factors of the first circle and factors of the second circle. Now this whole circle will select in such a way that this should come out to be 1 by x. That means in the numerator we should have 1 and the denominator we should have x. Suppose if you do not get 1 by x, then we have to reselect the whole circles and again try out. Don't worry, you don't have to reselect, because I'll tell you how to select the whole circles and you will select in such a way that it will be 1 by x always, because see here you have to select the whole circle in such a way that it will get cancelled. The factors of the first circle and the factors of the second circle will cancel out the factors of division and the factors of the differences. Okay, so in that manner you have to select it. So if it is, let's say, I'll show you an example, then you will understand better. So after this step is done, then in the second step, what we have to do is that we have to find out this 1 by x. We've got the x by a minus x by b, where a and b are the 2 whole circles we have selected and b is greater than a. So if we selected, let's say, 23 and 33 whole circles, then it will be x by 23 minus x by 33. This has to be bigger. So once you have done, and if you have neglected the common terms, then you get this fraction. So this fraction should be such that if we add or subtract depending on what it is actually coming, the compound movement, it should come out to be 40 by n. If it's not coming out, that means you have made some mistake. This is very important. So let's solve a problem and then you will understand in a better way. So you are required to divide 87 divisions, okay, by compound indexing, and the plates are given to us and we have to select 2 whole circles. We'll select 29 because 29 into 3 will be 87. So 29 has to be selected. By factors of 87 is 29 into 3. So we have to select 29 whole circles. And we have to select another whole circles on the same plate. 29 is in this plate, so we have to select another whole circles in this plate which has a factor 3, because 29 into 3, that 3 has to be get cancelled, because we want numerator in the we have 1 in the numerator, we want 1 in the numerator. So that 87 into 3, 29 into 3, that 3 has to get cancelled. For that we require to select another whole circles which should be we should have a factors of 3. So factors of 3 has 21, 27 and 33. So here I have taken 21. It can be 27 also, it can be 33 also. So once we have selected the circles in this manner, you will see that the numerator, all the factors will get cancelled and you will have 1 in the numerator. So here the factors of divisions required are 29 into 3, that is 87, and the factors of difference between 29 and 21 are 8. So we have 8 here, and the factors of 40 is this, and factors of first circle is 3 into 7 is 21 and 29 into 1 is 29. 29 is a prime number, so therefore we have selected a whole circle as a prime number. So 29 get cancelled, this 3 will get cancelled, these 3 2's and these 3 2's will get cancelled. So we have 5 into 7, that is 35. So my x is 35. So next step is x by a minus x by b. So b will be here 29 and a will be 21. So 35 by 21 minus 35 by 29, it gives us 114 by 21 minus 6 by 29. So we have to move one complete rotation and 14 hole in 21 circle, the crank and the plate both one complete rotation and subtract that in opposite direction and 6 holes in 29 whole circles. So this, since we are rotating one direction, then we are rotating in opposite direction, it is cancelling out. So therefore we can neglect this or cross out these common terms. So it is for movement will be 14 by 21 minus 6 by 29. So 14 by 21 minus 6 by 29, if you simplify this, and you should get 40 by 87, and that is what exactly we are getting. So we have done it correctly. So this is the first example. In the second example, okay, so same thing, same example. If we take 33 in place of 21, so 29 33, we get this. You can solve this, you will get 1 by 110. So similarly, this moment will be 23 by 29 minus 11 by 33, and third will be 29 and 27. So this is the solution. Okay, the next problem, we have to divide 77 divisions. So immediate LYS is 77 divisions. The factors placed in my mind 7 into 11. So we have to select two whole circles which has factor 7 and factor 11. So 11 has 33, so obviously 33 has to be there, and either I can select 21. Yes, we can select 21 only, no other is possible. Yes, 21. So 33 and 21. So 33 and 21 whole circles I have selected, and if you see the factors 7 into 11 and to 33 and 21 is 12. 2 into 2 into 3. So 2 into 2, they will get cancelled, this 3 will get cancelled, 7 will get cancelled, 11 will get cancelled. So we are left with 2, 5 and this 3. So that comes out to be 10 into 3, 30. So x comes out to be 30. So again x by a will be here 21 and b will be 33. So it comes out like this. So one complete rotation and 9 holes in 21 whole circle and minus 30 holes in 33 whole circles, or I can write it, so one complete rotations and this will be 1 minus 33 by 33, 33 by 33. This 33 minus 3 is 30 by 33, all the same. This common terms will get cancelled and this minus will become plus here. So 9 by 21 plus 3 by 33. So we are subtracting the common terms. So 30 by 33, I am repeating again, 30 by 33, in bracket I can write 1 minus 3 by 33, which is same as 1 full turn minus 3 by 33. So 1 full turn will get cancelled. So 9 by 21 plus 3 by 33, that means it should move in same direction. The plate and the index crank should move in same direction. That's why it is a plus sign here. So it is plus sign. If you add it, you should get 40 by 77. You should get 40 by 77. So that's it. We come to the end of the compound indexing. In the next lecture, we'll be discussing about differential indexing. So please don't miss out the next lecture. Thank you for watching this video.